Hi everyone, welcome to the ECE 101A review session for the midterm, and let's get started. So today we're going to be covering three main topics: electric and magnetic fields, phasors, and transmission lines, and you can expect all of these to be featured heavily on your midterm. So starting off with Maxwell's equations. So these equations relate E, which is the electric field intensity, D, which is the electric flux density, B, which is the magnetic flux density, and H, which is the magnetic field intensity to each other. And based on the question that you're given, it can be useful to express these in a variety of different forms. So these forms are listed here. It can also be useful to remember the electric potential, which is the negative gradient of the electric field. So these are just some useful things maybe to have on your, I'm not sure if you guys have an equation sheet, but it would be useful to be familiar with these equations. So the various quantities in these equations are related by the constitutive parameters, which is the electrical permittivity, the magnetic permeability, and the conductivity of a material. And so it will be very helpful to you to potentially know the units and maybe just know the values of these parameters. You don't really have to memorize them, but it would be good to sort of be familiar with them so that you can at least do like an order of magnitude check on any answers that you get. So to start, and next we have boundary conditions. So these are when you have an electric or magnetic field going from one medium to another. There's some conditions on the boundary of that medium that you need to be familiar with. So I'm going to go into some examples. This is just a useful chart. This is basically a repeat of some stuff that was present on the previous slides, but it's just summarized nicely here on this chart. So we're going to start off with our Maxwell's equation example, and also feel free to stop me if you have any questions. I can see the chat, and also if you just want to raise your hand or unmute and speak up, that's fine too. So for example 1, we're given a uniform sphere of charge centered at the origin with radius r0 and a volume charge density of rho v, and we're supposed to find the potential at all locations. So there's some important symmetries that we can just see reading the problem statement. First, the uniform sphere of charge is centered at the origin, so we don't have to deal with like any offsets or anything like that. And second, the volume charge density is given as a constant, so we can assume that it's uniform across our integrating variables and then potentially take it out of the integral and not have to deal with it being like a function of the radius or something like that. So let's get started. We have both the inside and the outside of the sphere to consider. So let's start with our variable r greater than the radius of the sphere. So this is the outside of the sphere. So we can use Gauss's law here and write down this equation. So this is just a direct application of Gauss's law, and you should just be able to write that down. And then we can start looking at the symmetry of the problem to see how we can simplify this equation. So we can see that the electric field is going to be symmetric across the surface area of the problem. And so that's going to translate into this field being outside of the integral over the surface. And then we can also see that the volume charge density is also symmetric over the volume, so we can remove it from the integral. And then these become just the surface area and the volume of a sphere respectively. And it would be helpful for you to also be familiar with those formulas so that you can just write them down. So you'll notice that I've used two different variables here, r squared and r naught cubed. So we're looking at the volume here, the charge contained within the sphere. And so that's going to be the complete volume of the sphere with radius r naught because we're outside of the sphere. However, when we're looking at the surface area, that's going to be the radius that we are currently at. So those are two different radii that you need to keep track of in this problem. So then we can write the electric field outside of the sphere just by dividing terms. And we can see that this field is in the r hat direction because it is symmetric in all other directions, so it has to be pointed radially outward. And then we're supposed to find the potential at all locations. So we can go from the electric field to the potential by taking the negative gradient. And we can notice that this electric field potential is only across one variable. So that means that we only need to do a single integral. And then just plugging in the value that we got in the previous part of this question. And note that the rho v r naught cubed over 3 epsilon naught, those are all constants. And so we just take them out of the integral and we can just integrate that and simplify to this expression. And then note that this is in units of volts. And this is also only valid for r greater than r naught. So this is when we're outside of this uniform sphere of charge. So the question says to find the potential at all locations, and we found when it's outside the sphere of charge. So now we need to consider when it's inside the sphere of charge. And so we're going to write down the Gauss's law formulation again. And the surface area integral is going to simplify the same way because the surface area of the sphere that we're working with is still not dependent on whether we're in or outside, but the volume is going to change. So instead of this being dependent on R naught, it's going to be dependent on our current radius, capital R, because the current radius is inside the sphere of charge. And so we're only getting like part of the contained charge of the sphere. So we have to use our current radius instead of the total radius of the sphere. So then we can simplify this to this expression. And now we have to do a similar method to find the potential. So we have the inside electric field, and now we need the potential. So we're going to integrate in the same way. However, this time we have to split the integral into two parts because we have the integral from negative infinity to r naught, which is the outside portion of the sphere. And then we have the integral from the edge of the sphere to our current sphere location because the electric fields outside and inside of the sphere are different. And so we need to make sure that when we're integrating across all of that space that we use the correct boundaries for when the electric field is defined that way. So you can go through and plug in the specific expressions. I'm just skipping some algebraic steps here, just in the interest of time. So like the previous expression, this is also in units of volts, and this is defined for the inside of the sphere. So now that we found the expression at the inside and at the outside of the sphere, so we found the potential at all possible locations for this problem. Does anyone have any questions? Okay. So moving on to the next example, this is unit analysis, and it's important for you to understand the units of the quantities that you're working with. So let's go through and simplify the units of this expression down to a single unit. So we've divided out the meters unit here. So it's just farads over henries. And so,
Could you scroll back for a second?
sure. So for the question, why we include both V in and E out and V E in for the V in, but not for the other one. So let's think about this problem. So when we're outside the sphere, let's say this blue circle is our uniform sphere of charge. And we're outside looking in, and let's say that this is our radius here. That means that everything that we're considering is the exterior electric field because we're going to be integrating in this way. Whereas when we're looking at the potential inside the sphere, we have our blue sphere here, but then our dotted radius is inside this blue sphere. Let's see if I can get a different color. Okay, it's like inside this blue sphere here. So that means that when we integrate in from negative infinity, we're integrating over the exterior of the sphere and also this interior portion. And since they have different electric fields, we need to integrate over the different electric fields. And so that's why we're considering both the exterior and the interior electric field when we're looking at the interior potential, but not the exterior potential. Does that make sense? Okay, great. Okay, so remembering the definition of farads is charge over voltage, and the definition of henries as volt-second squared over charge. We can simplify this down to a single unit like this. And then we can recognize the charge per second as amperes, as current, and then this is volts. And so this is going to be Siemens. So this is just looking at the units of the quantities that you're considering. So those are pretty important, and you should probably just be familiar with any units that you're working with. Does anyone have any questions on this problem?
Can you see the second slide again? The one that showed like the units of the stuff.
Sure. This slide?
Yes, please. Thank you.
I just took this table from your textbook, so it's there for your reference as well.
Oh, okay. All right. Thank you.
Okay, so let's move on to our next topic is phasors. And so phasors are useful when we want to look at how something behaves without considering its time-dependent component. And so this chart here is just a useful summary of different like phasor properties, like what happens when you take a derivative, and just different conversion methods that can be useful to remember so that you can quickly go through a problem. Now, transmission lines are where the phasors are applied. So in transmission lines, you have these two equations for the internal voltages and currents. And then you also have the reflection coefficient and the standing wave ratio are going to be some important parameters that you'll have to know how to find using a Smith chart. So we'll do an example of that. And then other important parameters are the impedance, the overall impedance, the input impedance, and what an impedance looks like when it is connected to a line, because due to the properties of a transmission line, if you have a shunt or an open, then that's going to appear differently if you're a certain number of wavelengths away from that impedance. And finally, two important wavelengths of a transmission line are the quarter wavelength transformer and the half wavelength. And so these are just some useful relationships to know so that you don't have to derive them if you're dealing with one of those specific types of transmission lines. And then it's also important to remember this power flow equation. So the incident and the reflected power are going to sum up overall to a percentage of 1. And so you're going to, if you're looking at a question that asks about power, which we'll do an example of, you can expect the overall percentages to and power to sum up accordingly. So let's do an example of transmission lines. So if we have a transmission line with this characteristic impedance of 100 ohms is terminated in this load, and we're given the peak value of the load voltage, what is the time average power dissipated by the load? So the first thing that we're going to have to do is find the reflection coefficient. So remembering the formula from the previous slide, we can plug in the given values of the problem. And you can plug this into your calculator and get this complex number expression. And then since we're trying to find the average power at that distance from the load, then we can use the equation for average power. And so note this term RL here is going to be the real part of the total load impedance. Okay, so in this expression, the 1/2 came from this 1/2 here, and then the voltage squared, that's going to be the 12 volts given in the problem as the peak load voltage, and then the 50 is the real part of the load impedance, and then the denominator is the magnitude of the load impedance squared. Does that make sense?
I'm sorry, what do you write in the squared part on the numerator? right next to
Oh,
this 50.
that's a 12. Sorry, it's a little messy. Yeah, the person in the chat was correct. I accidentally wrote a minus J100. Okay. So then we'll go on to the next part of the problem, which is what percentage of the power in the line is dissipated by the load. So for that, we can look at the overall power reflected equation. Okay, and then we can see that the ratio of the power to the load over the power of the forward wave, because this is the power to the load here, and then the ratio of the load power divided by the power of the incident wave on the transmission line is going to look like this. So that just becomes 1 minus the reflection coefficient squared. So we found that in the previous part of the problem. So we can calculate this as 61.5%. Does anyone have any questions on this part? Okay. So now we're going to move on to Smith charts. So Smith charts are an important tool to get the input and output impedances plus other useful parameters regarding transmission lines. And so some important things to note about the complete Smith chart is that the open circuit impedance is on the right, while the short circuit impedance is on the left, and it's reverse for admittances. So it's useful to keep track of what kind of quantity you're dealing with so that you know which part of the Smith chart that you're going to be using. So I think the best way to go through Smith charts is to look at examples. So I'm going to be finding some of these quantities based on the Smith chart here. So first, for the voltage standing wave ratio, we look at the normalized impedance. So that's going to be ZL prime. And that's ZL divided by the characteristic impedance, C naught. And so that's going to be 1 plus J.5. And so we're going to look for those lines on the impedance chart. So this circle here, this is 1. And then if we look at the 0.5 line, it intersects the 1 circle here. And so that's going to be the location of the impedance on this chart. And so now if we draw a circle around here, okay, that's a really terrible circle, but if we had drawn a nice circle, we would see that this intersects at about 1.62. So does that make sense to everyone? Okay, so for the reflection coefficient, you start from the center of the Smith chart, which is this point in the middle here, and you draw a line that intersects the input impedance and goes roughly to the top of the Smith chart. And so there's going to be two segments of this line that are important. The first is going to be the center segment, which I'll call OP. And then the second is going to be this longer segment, which is, I'll call this point R. And so the reflection coefficient magnitude is going to be OP over OR. And so when I measured this ratio, I found it to be 0.285. Next, the thing we need is for a complex number, you need a magnitude and an angle. So we found a magnitude and now we need an angle. And so this angle here is going to be read off of this like portion here. It's the second layer of the outer ring. And so we can just read off this angle to be about 75 degrees. So that means that we found our reflection coefficient because we have a magnitude and an angle. And so then you can just write that in whatever form, like if you want to write it in rectangular form or polar form. And then for the next part, we're going to be looking at the input impedance 0.3 lambda away from the load. So let's see if we can use a different color. So if we go 0.3 lambda away from the load, we're currently at about a little less than 0.15 lambda. And so if we're adding 0.3 lambda to that, we're going to be around 0.45 lambda. That's going to be our new location. And so if we look at this location here and draw a line from the center of the circle to this location, then we can look at where it intersects and see that we have an input impedance. It's going to be, we can see that we have an input impedance that's going to be about 0.58 and an imaginary portion that's going to be about 0.37 because that's where we're intersecting this blue circle here. And so if we take those, that's just reading off from where this line comes in. It was a little different when I drew it and had a slightly better drawing, but that's all good. It's honestly, Smith charts are, if you can draw it correctly, then if you have like a ruler, that would be super helpful. So then we're going to multiply by the characteristic impedance to convert back from our normalized impedance to a standard impedance that you would actually use. So this is going to be our input impedance at 0.3 lambda away from the load. Does anyone have any questions?
So the 75 degrees is measured from the flat real line, right, on the right, up
Yes,
to the
so
red. That's 75.
the red point R, it intersects the, like this inner outer circle, I'm not sure how to call it, the angle of reflection coefficient in degrees circle. It intersects between 70 and 80, so I'm calling that 75 degrees. Obviously, if you had a ruler, you could look at the chart and get a more precise bearing on where that intersection is. Okay, so that's how I found theta. And then I'm not sure what your question means, Christopher, if you want to speak up. Okay. Okay, so I'll explain ZLN. So that's when we rotated this red line here, we rotated it 0.3 lambda around and we drew this line into the center. And so when we drew this line into the center, it intersected this blue circle here. And so we found the point of intersection with the blue circle. And then we followed the point of intersection with the blue circle to the edge of the chart. And I guess in this rendition, it's closer to minus J.2. And then if we follow it in, it's around like 0.61. So we can change our answer to reflect this drawing on the Smith chart. And then we would take 50 times that to get the unnormalized value. Does that make sense? Okay, great. Does anyone have other questions? Okay, so another important thing that you can do with Smith charts is stub matching. So that's going to be taking an impedance where you're looking in at that impedance or something like that, and then you're going to be adding some sort of shunt across that to get rid of some unwanted inductance or capacitance in your transmission line. Typically, you're trying to make your transmission line totally resistive, so you don't have to worry about like any energy storing components. So step matching is a great way to do that, and this is a sort of recipe for how to do that. So the first thing you're going to do is normalize the impedance and then find that impedance on your Smith chart. And then for parallel stubs, you're going to want to do a 180-degree rotation because you're going to be looking more at the admittances. And then for series stubs, you're going to be sticking with the impedances, so you don't have to do this 180-degree rotation. And then you're going to figure out where you are on the Smith, where you are like the point on the Smith chart, and then figure out what your imaginary component is, and then figure out what you would need to add to get rid of that. And then you can reflect this across the axis and then read out the reactance that you would need to add. And then the length L is from the reactance to the open circuit series stub, and then the short circuit parallel stub, the short circuit series stub, or the parallel open circuit stub. So it just depends on what kind of problem you're working with, like what the L is going to be exactly. So we're going to do an example to show you this. So if you have a 25 ohm antenna and it's connected to a 75 ohm lossless transmission line, you want to illuminate reflections back toward the generator by adding an impedance Z at a distance L from the load. So this problem is looking for the impedance Z and then the shortest distance L. You can actually add like a lot of distances of L just by keeping going around the Smith chart, but you typically want the shortest distance of L. And so to start off with this problem, we're going to normalize the impedance. And then since we're working with a parallel system, we're going to be looking at admittances. And so the normalized admittance is 1 over the normalized impedance. So that's going to be 3 here. So then we're going to look at our Smith chart and find the impedance 0.3. So that's going to be right here. on our Smith chart. And then we are going to attempt to draw a circle. Okay. Okay, we have a circle, and then we are going to look at where our circle intersects the one circle here. It's one of the most important circles on the Smith chart. So when we look at where our circle intersects the one circle, the shortest distance away from that, if we look at the 0.25 lambda where we're starting here, and then if we look at the shortest distance away, if we go clockwise around the circle, that's going to be this intersection point here, as opposed to this intersection point here. So we're going to be looking at this lower intersection point for the rest of this problem. So then we can see that this point here is going to be 1 minus 1.2 because we're pretty close to the 1.2j line on the chart, which is here, and then we're on the one circle. So if we have an input impedance where we're looking in and we're seeing 1.2 minus 1.2j impedances. So if we look at this expression and we want to, explain why it's the closest one more time. So we're starting from the 0.25 lambda point and we're going clockwise around the circle. And so if we go clockwise around the circle, then the point that we get closest to first is this lower point, because to get to this upper point, we would have to go like 3/4 of the way around the circle. And that's longer than about 1/4 of the way around the circle. So that's why it's the closest point. Okay, so now we have this input admittance and we want to get rid of this imaginary part. And so the way that we would get rid of this imaginary part is we want to add this J1, a J1.2 quantity so that it cancels with this negative J1.2 quantity. And that would just leave us with a completely resistive transmission line. And so since we know what we want to add now, we can normalize this. And then if we want the impedance or the admittance, depending on what the problem is asking for, we can just convert that. So we now have this new impedance that we're adding, which we found the value to. And then we need to find the distance L from the load. And so that is just looking at where, let's see. If we start from the center point and we draw a line that intersects with this point, we get, this is about 0.33, let's see, that's like 6 lambda. And then our starting point was 0.25 lambda. And so the distance L here, L equals 0.336 lambda minus 0.25 lambda, which equals 0.084 lambda. And that's going to be in meters. Does anyone have any questions about this part? Okay, great. So that was all of the important topics that I thought would be helpful for your midterm tomorrow.
Hello.
Hello.
Isn't Y new already normalized?
So Y new here is going to be the normalized impedance, but if we want to add like an actual capacitor or inductor to the circuit, then we need to be looking at actual values. So here we're denormalizing it, and that is dividing by Z naught because remember, admittance is 1 over impedance.
Oh, okay. We're denormalizing it, all right?
Yeah. So Z new is 1 over Y new.
Quick question, how would we watch this recording in the future?
So this recording will be posted to the HKN YouTube channel. So you should be able to view it there. It will probably be posted in the next couple days.
Okay, dope, thanks.
How the output. Yes, I'll upload the slides to the HKN Discord server in the 101A channel. Okay, example 3. Okay, so I'm going to stop the recording, but I will stick around for a few questions.